Let's dive into some of the most simple examples of polymer materials, and those are the hydrocarbons. Hydrocarbons are polymers that are organic, right? They contain carbon. These have covalent bonding. So, for example, we know that carbon wants to have 4 bonds, right? Every carbon would like to be bonded to 4 things, right? Because it has 4 electrons available for bonding, right? Each of these 4 electrons is available to form a bond with something else. So you can have single bonds, right, that it forms. It can form double bonds, or it can form triple bonds, right? If it wants to share more than 1 electron, it can do double or triple bonds, okay? However, a carbon hydrogen can only have a single bond, right? So if you have the example of methane, methane is CH4, so it's a single molecule. It's the smallest hydrocarbon. You've got carbon, which has 4 electrons that it's willing to share, but each hydrogen only has 1 electron. So if hydrogen only has 1 electron to share, then at best you can get a single bond. You can't form a double bond because hydrogen's only got 1 electron, right? So in order to form double bonds or triple bonds, you have to have other things than just hydrogen. And so what you can have is additional carbons, right? So for example, let's look at acetylene and ethylene, right? Ethylene first. Ethylene is this. It's got carbon double bonded to another carbon, and then it's got hydrogens. Now I'm going to have 2 hydrogens bonded to each carbon. Why? Well, because let's count the bonds. You've got 1 bond, 2 bonds, 3 and 4 bonds for that one. So it's satisfied, right? So each of these carbons has 4 bonds, and it accomplishes that by having this double bond. And what do you know about double bonds from Gen Chem? Well, whereas these bonds can rotate, right? That hydrogen can spin, right? We know that this is not able to rotate. That is a rigid bond. So you would not be able to, for example, rotate this whole group around that bond. You wouldn't be able to rotate it. It wouldn't be allowed. It's a rigid bond, right? Okay, that's an example of the bonding differences between single and double bonds. And then acetylene. How would acetylene look different? Well, now you've got a triple bond. So you've got carbon and carbon with a triple bond between them. So how many hydrogens can they have? Well, each carbon wants 4 bonds, and right now they've each got 3, so they only need 1 more each. So you end up with this molecule, acetylene. This is now a linear molecule. It's completely linear, whereas this one is a planar molecule, right? This thing sits in a plane because this is you've got these 3 bonds right here, right? So that's going to sit, they're going to spread out equally, and they're going to do that by being roughly 120 degrees apart. Now, it's not exactly 120 degrees because the double bond has a different electron density than the single bonds, but you could approximate it as being 120 degrees between those. Okay? We call these hydrocarbons saturated, and you've probably heard about this, saturated versus unsaturated fats. What that's referring to is whether or not there are double or triple bonds. It is unsaturated if you've got double or triple bonds. It is saturated if there are only single bonds, right? Sometimes we call these hydrocarbon molecules, atoms made up of just hydrogen and carbon, we call them paraffins, right? And so the number of carbons in the paraffin can change the properties. For example, let's start with methane. Methane is just carbon with 4 hydrogens. Sometimes, by the way, you leave off the H's and they'll just put the dash marks. I'll try and remember to write the H's, but if you see them not there, that's pretty common. We already showed you ethane. What about propane? Well, propane would look like this, where you've got 3 hydrogens on the end of each of these. But this middle one would only have 2 hydrogens. And we know that because we can count the bonds. Again, each of these carbons has to have 4 bonds, and the way that we've drawn it, it's got 4 bonds, right? And then you could move to butane and pentane and hexane. So this word right here is telling you how many carbons are present, right? In hexane, you're going to have 6 carbons. So 1, 2, 3, 4, 5, 6. Oftentimes, when you do polymers, they won't write the C. Instead, they'll write this zigzag line. So what does this zigzag line mean? What that zigzag line means is that they're not drawing the carbons, which would be right here. And then they're just not even drawing the hydrogens, which we know would be these single bonds. And again, I'm not even writing the H, I'm just putting the bond. So this is a type of organic chemistry shorthand that, I didn't make the rules, it's just what people often will do. Okay, that would be hexane. Now, why did I draw it a zigzag structure instead of a straight line? Well, because remember, if there's all single bonds, then each carbon has 4 bonds, right? So if you've got your carbon, let's imagine where those bonds would be. Right? So here I'm drawing 1 hydrogen above, 1 hydrogen to the left, 1 hydrogen coming out towards the viewer, and then 1 hydrogen going away, right? It's a tetrahedron, right? We've seen this before. We saw it last chapter in crystal structures, right? This forms a tetrahedral shape, right? Where that carbon is in the center and it's being surrounded equally by 4 atoms. Therefore, it has to have this sort of tetrahedral shape. What you're seeing here is that tetrahedral shape represented in the zigzag pattern, right? These bonds, the bond angle between these would be 109.5 degrees, and you would have seen that in Gen Chem, I think, at some point. That is the bond angle when you have single bonds, 4 bonds around a carbon. Okay? So, last thing to cover with hydrocarbons is their properties vary with the chain length, right? As you increase the number of carbons that go along this chain length, for example, going from methane, which is 1, propane, hexane, increasing your carbon, you see a trend in their properties. For example, here you see melting point down here. Here's your melting point, and then you've got your boiling point. And the trend for both of these is an increase. They both go to higher temperatures as you move towards longer and longer chains. Why is that? Well, think about it. These chains look like this, right? What kind of bonding is holding those together? Because when that bond breaks, now you get that it's boiling, right? When those things are held together, it's in a liquid state, right? When there's some sort of bond between these things, it's held together, right? In a solid or in a liquid. To melt it or to boil it, you have to break those bonds. So what sort of bonds are we talking about? Well, these are not covalent bonds holding these together because these are long strands of independent chemicals. So what we must have is, let's say you've got a slight positive charge and a slight negative charge. That forms a van der Waals, or a secondary bonding. And these are pretty weak. However, the longer these chains are, the more they line up, the more of these bonds you can get across there. So the bonding increases with number of carbons. Therefore, the boiling and melting points should both also increase. Now, the way that I've drawn these is linear. They don't have to always be linear. You can end up with different what are called isomers. For example, you've got isobutane and butane. Butane is 1, 2, 3, 4 carbons, right? But isobutane looks like this. Also has 4 carbons. Again, we could draw the carbons if we wanted to. There are 4 carbons, right? In both of these molecules, you've got 4 carbons. But they're going to have different properties. Isobutane versus butane. Why is that? Well, because remember, we're trying to line these things up. A butane molecule can more easily line up with another butane molecule and get that bonding between them, right? So that's going to have a higher melting point than isobutane, which has these side groups, which makes it hard for it to line up with things. So it's not going to have as good of bonding. So you would expect a higher boiling point for butane than isobutane. And sure enough, if you look it up, you'll find that that's actually true.